Students, in this class, we will be talking about data types. Now, what I'm going to do is I'm going to explain to you the different available data types in R. So to start off, we got numeric types, and we got a string, that is character type. We got Boolean. So Boolean would take values like true or false. And then we got another very important data type, which is called as complex numbers. Now, in most of the programming language, handling complex numbers is not going to be easy. But in R, you will understand the fluidity in handling complex numbers is so much better that you will hardly be able to find any language to surpass its ease. So having mentioned that, I'm going to give you an example with numeric data and with complex numbers or complex data. So let's get it started. So first what I will do is I will show you how numeric data are added. So of course I've already demonstrated this, so I will want to couple this up with other examples as well. So suppose you got number 54.78 and you got number 2 to be as 12.90 and you got number 3 to be equal to number 1 plus number 2, and you want to print number 3. So the value is 67.68. Now what if number 3 is equal to number 1 divided by number 2? And then you want to print number 3. So that is going to be 4.246512. Now what if number 3 is equal to number 2 slash number 1, and you want to print number 3 down? So this is the value. So you don't need any declarations such as float or integer to have the output. In R, the values of the output is obtained with such ease. Now, having mentioned this, let me move on to another example. Say I have this, say, Control L. I'm cleaning the screen, and I have a variable k is equal to, I have a string of numbers. In fact, it's better to say sequence of numbers, say 1, 2, 3, 4, and then you have m to be equal to c. You need to have the c there because that's the syntax. So c of 2, 3. Now what I want to do is I want to evaluate this expression. So p is equal to foremost, say, k plus 2, and then I am printing, say, p there. So in this case the values would be, the values of k is 1 added with 2, that's going to be 3, 2 added with 2, that's going to be 4, and 3 added with 2 is going to be 5, and then 4 added with 2 is going to be 6. So these are the values. This is for this expression, right? Now what if you want p to be equal to, say, k, I want to place it in parentheses, k multiplied with m. I'm coming out negative, or let, just for the sake of convenience, positive 1, and I'm printing p. So in this case k takes the value 1, so 1 times 2 is 2, 2 added with 1 gives 3, k takes the value 2, 2 times 3 is going to be 6 added with 1, 7, and then k takes the value 3. Now m takes the value 2 now. So 3 times 2 is 6, again 7, 6 added with 1 is 7. Now it takes the value 4, and m takes the value 3. 4 times 3 is 12, 12 added 1 is 13. So that is the output for this. Now what if you want to extend this? So the sky is the limit for your thought process or for your creativity. Because if I were to say P is equal to, imagine I want to calculate E is equal to MC squared, that is the expression. So in this case, I take M to be as K times C squared. Again, I multiply C. The C squared is going to be M squared. So M times M. So for sake of convenience, I'm using this expression and I'm typing P. Of course, I will demonstrate how the power is calculated as we move up. So this is exactly the result for the value for that particular expression. P is equal to K times M. Now we can now introduce complex numbers. So I'm going to introduce complex numbers. So let me have Z1. Z1 is equal to a complex number, say 5 positive 6i, and Z2 is equal to 2 positive 3i, complex numbers, and I want them to be added. Say Z3 is equal to Z1 added with Z2, and then I'm getting the output as Z3. So clearly 5 plus 2 is 7. The real part gets added together, imaginary parts gets added together. So that's why you get 5 positive 2 is 7, 6 positive 3 is 9. Now this is a beautiful example of the power of, to demonstrate the power of our language. If we were to write the same program in some other language, then of course this is not going to be so easy. Right. Now let us further extend our domains of examples. So now let me just declare Z1 to be equal to C of two complex numbers, say 2 positive 4i, comma 4 negative 3i. So 2 negative 4 negative 3i, two complex numbers. Let me introduce one more complex number. 7 is also a complex number. Okay, so of course the imaginary part is missing, but that doesn't mean it's not a complex number. So now the next number is C2 is equal to C of 1 positive 3i, comma 8 positive 9i, comma say 5 negative 2i. So this is a complex number. So Z takes the complex number, first one 2 positive 4i, and then 4 negative 3i, and then 7. Z2 takes the complex number Z1 positive 3i, and then 8 positive 9i, and then 5 negative 2i. Okay, so now let me just do this. So Z3 is equal to, now if I were to take Z1 plus Z2, you can now understand the power of our language, how it is applies its intelligence to exactly add real parts with real, imaginary parts with imaginary parts. So now if I were to say Z3, it will give me the three complex numbers. The first one, real part is added, 2 plus 1, 3, 4i plus 3i, 7i, and 4 positive 8, 12, and negative 3i positive 9i is 6i. And second case, real part is there, 7 positive 5 is 12. Of course, imaginary part is not there, so it's going to be negative 2i added with 0. So this is how the language of R treats complex numbers, which is in a way powerful